Okay, let's get started. So today I want to actually show you the details of the analysis of the MARC algorithm. That's the randomized algorithm for paging, which gets log k competitive ratio, where k is the size of the cache. Can people hear me? Yeah. Oh, do I have a scribe for today? Okay, good. And then I want to show you kind of a generic framework for analyzing and coming up with online algorithms based on this. There's a primal dual framework, as it's called. So this is something that was developed by Buchbinder and Naur, I guess, in 2005. Okay, so today we're going to see 2 HK competitiveness for randomized paging. This is the MARC algorithm. We'll also see online primal dual. And as an example of how you use this to develop good online algorithms, I will show you, again, the ski rental problem. So remember, last time we saw, for the ski rental problem, you can get a 2-competitive algorithm. Okay, I'll re-show you that same algorithm, but in this primal dual language, which I haven't defined yet. Okay, that's just an exercise to get you comfortable with the language. And then I'll show you that you can actually beat the ratio 2. Okay, if you allow yourself to be randomized. So you can actually get a competitive ratio of e over e minus 1 if you use a randomized algorithm. Okay, and that's that result is not due to Buchbinder and Naur. It was already known before by Carlin and others, but it falls out more naturally from the primal dual framework. And then we'll also see, so we'll see here e over e minus 1 competitive ratio. And we'll also see online set cover. So there are these M sets, but in the beginning you don't know what items are in the sets. You just know their names. They're set 1, set 2 up to set M. And online you see an item. You see the items one by one. And when you see an item, you have to make sure it's covered. Okay, so if it's not already covered by one of the sets that you chose, then you need to pick a set and cover it. Okay, and at the end of the day, you want to compare yourself to opt. So I'll maybe say a few words about set cover before I give that analysis, but I hope, who here has seen set cover? I covered it in CS 124. Who has not seen set cover? Okay, so I will define the problem. Okay, who here has another thing? So this is also something in 124, which I'll do a very brief recap. But who has seen linear programming? Okay, who has not seen linear programming? Who doesn't know what a linear program is? Okay, so I'll give a very brief introduction. So this whole online primal dual thing is built around linear programming. Okay, so linear programming formulations of problems. So I will say a few words about LPs before I get into that, but you need to. So it's all about LPs. Okay, so the MARC algorithm. This algorithm is due to Fiat and others. Journal of Algorithms, I think 91. Okay, so remember how this works. This is a particular implementation of the 1-bit LRU from last time, but where when we evict an unmarked page, we choose an unmarked page uniformly at random from the set of all unmarked pages. Okay, so initially, all pages are marked. Okay. When we bring page P into cache. We're going to evict a uniformly random unmarked page. Then mark P. Now, it may happen that eventually all the pages are marked. If all of the pages are marked, so there's no unmarked page to evict, unmark all of them. And we'd like to say that the expected, the competitive ratio of this randomized algorithm is 2 times the kth harmonic number. Remember, this number here is 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over k, which is natural log of k up to a constant. Okay, so you can see this by comparing this sum to integrals in both directions. Yeah? Say that again? Yeah, unmarked. Thank you. Although, to be honest, it doesn't really matter in the beginning, yeah, because you just unmark them all. So. OK. And if all the pages are marked during a request, then outside of cache. OK, so the way that we are going to analyze this algorithm, and I think I started saying this at the end of last lecture, but I didn't get to actually prove anything, is we're going to divide time into phases. Okay? A phase starts when we unmark all pages. And a phase ends when all the pages are marked and someone is just about to make a request to a page outside the cache. So we're about to unmark all the pages and start a new phase again. Okay, so analysis will divide time into phases. A phase starts when we unmark, or a new phase starts when we unmark all pages. OK, and I think I defined 2 terms that are going to be used in the proof at the end of last lecture, but I'll remind you. So definitions. OK, so a page is clean. And let me call the, I don't want to write mark all the time. So for me, M is the mark algorithm. Algorithm M is mark. So a page, let's say a page P is clean if P wasn't requested. So being clean is also time sensitive. You're clean at a particular time. So a page P is clean at a particular time if P wasn't requested in the previous phase and not yet requested this phase. OK. And another kind of pages that we're going to look at is a stale page. A page is stale if it was requested last phase, but not yet this phase. OK. So except for maybe the last phase, how many distinct pages are requested in a phase? OK, so let's introduce some variables. So let L be number of clean, or let's say Li be number of clean pages requested in phase I. And I can call it Si, be number of stale pages requested in phase I. And we know that SI is just equal to K minus Li, as you just said. So we're going to introduce some more notation. OK. So we need to compare opt against M, against the Mark algorithm. And we're going to do it phase by phase. OK. So we're going to say that phase by phase, the gap between them is a factor of 2 times h sub k, plus some stuff that telescopes across phases. So more notation. Let D be the number of pages. Let me make sure I don't mislead you. In opt's memory, let's say DI. DI is the number of pages in opt's memory at beginning of phase I, which aren't in Mark's memory, Mark's cache. I've been saying cache. Let me be consistent. Okay, so this is some non-negative number. And let di prime be the number of pages at the end of phase I. Right, so in particular, di prime is just d sub I plus 1. Interrupt me if you have any questions. So what we will show opt pays at least I think I'm going to say 1/2 L plus di prime minus di in phase I. That's the number of misses, cache misses, that opt has. And 2, expected cost of Mark in phase I will be at most hk times L. Okay. And it will follow from this y. So 1 implies over whole sequence opt pays, let's say the sum over I well, L over 2 plus, this is just di plus 1 minus di. So this is just the sum over I of L, well, let's say Li over 2 plus d final minus d initial. So what's d initial? I didn't say it, but 0, right? So I'm assuming that that everyone starts with the same contents of cache in the beginning. Otherwise, there's no hope to be competitive, because opt might start with all the things you're about to ask for, and you start with none of the things that you're about to ask for, right? So we're assuming that they start with the same things in memory, which means that initially there is no difference. So opt pays at least this. This is positive, so this is certainly at least the sum over I, Li over 2. Sorry, say that again? There's 1 over 2. Yeah, thank you. Whereas this is paying hk times the sum of li. So the fact that, the gap is a factor of 2 times hk. Okay. And in that paper by Fiat et al., there's a lower bound which says that no randomized algorithm can do better than hk. Okay. So you could ask, well, is hk achievable? And in fact, it is. There's a paper by, I'll write it at the end of this, by McGeoch and Slater, two names we've already seen, that gave an hk competitive algorithm, which they called the partitioning algorithm. I'm not going to cover it. And afterward, there was another simpler algorithm given by Aklioptis et al. That also achieved hk competitive ratio. Okay, so I'm not going to go into either of those, but I'll insert that into the references of the lecture notes. Okay, so 1. Okay, so proof will show that opt pays actually the max of Li minus di and di prime. Okay, and the max is certainly at least the average. That's where we lose the factor of 2. Okay, so why does it pay at least Li minus di? Well, I mean, it's almost immediate from the definitions, right? So remember, the Mark algorithm doesn't have any of these clean pages in its cache at the beginning of the phase, right? So for each of these clean requests, the Mark algorithm has to bring it in to service the request. Whereas, how many of these clean pages can opt possibly have in its cache at the beginning? Well, di, because it only differs on di. Right, so opt only has at most di clean pages at the beginning of phase. And why does opt pay at least di prime? That's also something simple. Okay, so tell me, at the end of a phase, describe to me, what are the pages that Mark has in its cache at the end of a phase? Yeah, the set of pages that were requested in that phase, right? And you're telling me that opt doesn't have exactly that set of pages in its cache. It has some, there's some difference. It has some di prime pages besides the pages that were requested in that phase. Okay? So it's essentially operating on a cache. Well, that means that for di prime of those requested pages, there had to have been an eviction. Okay. So at the end of phase, Mark has the set of pages requested in that phase in its cache. Right? So, and opt also had to bring those pages in. Right? So if there are any differences from that, it's because there was an eviction. Okay. So any of opt's d prime differing d prime I differing pages corresponds to an eviction. Okay, good. How about 2? Okay. So there are two types of requests that I'm going to look at, which are clean ones and stale ones. Okay. In fact, those are the only kinds of requests which can cause an eviction for the mark algorithm. Right? Only clean and stale requests cause eviction for mark. Right? Because if you've already, what does it mean to not be clean or stale? It means you've already been requested in that phase, which means mark already has you in its cache and you won't be a cache miss. So mark pays, how many evictions are there for clean pages in the mark algorithm? Li. Mark pays Li misses for clean requests. Right? I mean, clean means it wasn't asked in the previous phase, which means that mark doesn't have it in its cache. So it has to evict something to make room for it. So now, we haven't said anything about randomness yet. Now we're going to talk about what happens with stale requests. Okay. So there are, okay, so let's say we have had S stale requests and C clean requests so far. So we're at a point in time. We've had this many requests so far in the current phase. And we're about to make the next stale request. Okay, so what does cache look like? So let me draw M's cache. It says size k. So how many of those clean pages are in the cache? All of them, right? So nothing that's been requested in this phase is kicked out. So this is all taken. C clean ones are taking up spots in cache. Also, the same things is true for the S stale requests that have happened already, right? Those S guys are also in cache now. S stale. So what can you tell me about what kinds of pages are these? The pages that are left here. They're stale, exactly. They've been requested in the previous phase, but not yet in this phase. They're stale. Okay? And what can you tell me about, right? So remember, when these things are brought in, random things are evicted. So this is a random set of stale pages that still exist, right? Okay. So this is a random set, random subset of the remaining stale pages. And what's its size? Well, its size is just whatever's left, k minus s minus c. Okay. So probability that, so the expected cost of this new stale request is just the probability that this page hasn't been kept, which is equal to 1 minus the probability that it has been kept. And what's this? Well, initially at the very beginning of the phase, there were k stale pages, right? All the pages from the last phase. So what's the chance that our one page is one of the k minus s minus c pages that are left? This is just k minus s. I feel like I am not saying the right thing. So I want to say the page that has been kept, the probability that it's been kept is k minus s minus c over k, but that doesn't sound right to me. So I seem to have said to myself that this thing should be c over k minus s. Okay. Sorry, say it again.
That would be equal to 1 minus k minus s minus c over k minus s.
Because there are only like k minus s stale pages remaining, right?
Yeah, that's exactly. Okay, good. Yeah. So okay, good. So there have been s stale requests, which means there are k minus s stale pages that still remain. Okay. And so the question is, what's the probability that one of these c clean requests clobbered me? And that's c over k minus s. Okay, good. I'm not going completely crazy. Okay. Which is certainly at most, let's call it L times 1 over k minus s. Okay. Okay, good. And remember now, s, the number of stale requests we said was k minus li. So s is ranging from 0 up to k minus li minus 1. Right, let me just write that here before I start a new thing. So expected cost of all stale requests is equal to, or is at most, L times the sum going from s from 0 to k minus li minus 1 of 1 over k minus si, which is exactly the sum, L times the sum from j going from, so it starts at li minus 1, li plus 1, right, up to k of 1 over j. Right, so when s is 0, this is 1 over k. This is s. When s is 0, this is 1 over k. When it's this, it's li plus 1. And this is exactly equal to the L times the kth harmonic number minus the li plus first harmonic number, or the lith harmonic number. Okay. which is certainly at most, this is li, which is certainly at most lihk minus li. So that cancels that. And the total cost in a phase is exactly li times hk. OK? Questions? OK. So I'll say something about, maybe an open problem. There are final projects in this class, so I'll say something about that, and also, things that have been done since then. And then I want to move into this primal dual stuff. Oh, and maybe I also want to show you why you can't do better than, I won't get the right constant, but why can't you do better than log k? Okay, why can't you do better than a log k competitive ratio? Let me say something about that. It was also in the Fiat et al. Paper. So theorem, any alg has competitive ratio omega log k. Okay, proof. Let the number of pages in the universe be k plus 1. Okay, and our request sequence is uniformly at random length m. Okay, so what's the expected cost of any algorithm? Sorry? To serve the entire sequence. So we have the sequence of length m. At every step, the request is a totally random page from 1 up to k plus 1. Sorry, m what? I like what you said except for the times k. So I claim, right, the expected cost of any algorithm is exactly m over k plus 1. Right? When a new page comes, I have to pay an eviction if that's not one of the pages I'm holding. But it's a uniformly random page. Out of k plus 1 pages, I'm only holding k of them. So the probability that I don't have this page is exactly 1 over k plus 1. Meanwhile, opt, right? Opt, even though it's a random sequence, opt gets to see the entire random sequence from the beginning. Okay? Opt gets to see the entire random sequence from the beginning. Or maybe the right way to think about this is, what I really showed is that for any algorithm, no matter what your algorithm is, there exists a sequence, a request sequence of length m, such that your algorithm will pay this on that sequence, right? So there's actually one sequence which will trip up your algorithm. In particular, a random sequence is expected to, so there exists a sequence which will. Okay, so that's what this means. For any algorithm, there is a sequence which will trip up your algorithm and make it pay this, a length m sequence. Meanwhile, I claim that for this random sequence, opt doesn't pay that much. Why? So let's say that opt now has an eviction, right? So what is opt going to evict? I mean, I claimed that the min algorithm was optimal. You don't even need to know that it's optimal, but consider the algorithm which evicts the thing farthest in the future. Okay? So it has something that it needs to evict. It's going to evict the thing farthest in the future. What has to happen for me to see that page in the future? Every other page had to have been requested before that page. So the question is, if I'm picking random numbers between 1 and k plus 1, how long does it take me to see every single number? Which is known as the balls and bins problem. I'm not going to analyze it, but you need k log k, basically k log k numbers in order to see everything. That's called the coupon collector problem. Okay, so when op evicts a page P, it doesn't fault again until P is seen again. If we evict the farthest in the future, that implies that all other pages were seen before P. Okay. And the expected time to see all numbers in the set 1 up to k plus 1 is theta k log k. Okay. So you can view this as saying any algorithm will fault at least a 1 over k fraction of the time. Opt only faults a 1 over k log k fraction of the time. Right? So opt is better than you by a factor of log k. Okay. If you're uncomfortable with the fact that the sequence is random, look, you can say the expected cost is at most this. So in fact, 2/3 of random sequences will make you cost at most 3m over, or let me say it like this. Expected cost of any algorithm is that. Well, you need to be a little more careful. But basically the point is you could try and give a concentration argument and say that there are actually a good fraction of pages that make you cost around this. And there are a good fraction of pages for which sequences for which this is true. A good fraction of sequences make you pay around this. A good fraction of sequences make you do this. So there's something in the intersection. Okay. Anyway. That's all I wanted to say about analysis for randomized paging. And I did mention that in what's after this, there's McGeoch and Slater. In Algorithmica 91, achieved competitive ratio exactly hk as opposed to 2hk. And there was a simplification later in Akleopsis et al. Both a different algorithm and a simpler analysis. That was theoretical computer science in 2000. One other thing, which as far as I could tell seems to be open, but I can't, yeah, papers didn't mention it as being an open problem, but I couldn't find any reference which actually solved it, which is suppose opt has cache of size h, whereas U have a size of cache k. So remember with LRU, I said LRU is k competitive, but I didn't prove it. If you have a cache of size k and opt has a size of cache h, then LRU is actually k over k minus h plus 1 competitive. Okay, which means if the opt has half the cache to work with, then you're too competitive. Okay, so you could ask the same thing for, the randomized setting. So if opt has a cache of size h, then Neil Young in SOTA of 91, I believe, showed you can get 2hk over, actually, what's the exact bound? 2 ln k, 2 ln, 2 times ln of k over k minus h plus 1 competitive. And he also showed that getting competitive ratio better than ln of k over k minus h plus 1 is impossible. Right? So when h equals k, that's what we just covered. When h equals k, that gap of 2 has been closed by McGeoch and Slater. But when you introduce this resource augmentation point of view, resource augmentation is the phrase or the jargon that's used for you have a cache of size k and opt has a cache of size h. Okay. Under resource augmentation, it seemed like that gap of 2 has not been closed because, in fact, Young's paper cites this paper. So it came after it. He knew that the gap of 2 was closed there. He even mentions it. But he has the gap of 2 in his own paper. So it seems like an open problem as far as I'm aware. OK. I'm not really going to get into it, but paging is actually a special case of a more general problem called the K-server problem. So paging is a special case of what's called the K-server problem, which itself has quite a long history and some big open problems. So the idea here is your algorithm controls k servers. And also there are endpoints. There is an endpoint metric space. Okay, just think there are endpoints and a distance function. Okay. So request sequence is a sequence, call this metric space x, is a sequence of points in x. And when someone requests a point P in this space, you must move a server to lie on P. Okay, so your K servers are always living on some K points. Okay? And then when someone requests a point, if a server is already on that point, you don't have to do anything. If a server is not on that point, you have to choose which server to move there and move it. And what do you pay? You pay the distance. Right? If it's already at some point Q and you're moving it to P, you pay the distance from Q to P. Okay, so, and you want to compare yourself to opt. Okay. So 2k minus 1 competitive deterministically is known. This is due to Papadimitriou and, did I not write it down? This is called the work function algorithm. Maybe I didn't write the reference. This is Koutsoupias and Papadimitriou. And this was in JCM 95. And it's known that you cannot beat K competitive with a deterministic algorithm. So there's a factor of 2 there, which has been open since, back in the day. This is the journal version. The conference version was even earlier. So getting rid of that factor of 2 has been open for more than 20 years. So you could ask again, can we do better than K or theta K with a randomized algorithm? So an open question is to get a randomized algorithm with competitive ratio polylog K. In fact, I think people believe that the right answer should be log K, just like for paging. Okay, and there was quite a big breakthrough in this area very recently where they didn't get polylog K, but they got polylog K, polylog N. So Bonsall, Bookbinder, Madri, and Naor, this was just in 2011, they achieved ratio which is log K squared, log N cubed, log N. Okay, so it has a dependence on N, but people believe that there should not be any dependence on N. You should be able to just get polylog K. Of course, you can get a dependence on K independent of N, but there's that K. I think randomized you might be able to beat that, but still it's not anywhere near polylog. And I don't know all the details of this, but I'm fairly sure that it uses the primal dual framework of Bookbinder, not where I'm about to tell you. Oh, and people see why this is a generalization of paging. So the endpoints are your pages. What's the metric? What's the distance between 2 points? It's 1. All the distances are 1. Okay. Another thing more general than simply paging, but less general than K-server, is weighted paging. So the idea is not all pages are created equal. Okay, so some pages live on the network at some other machine, and you have to pay a lot to bring them over the network, whereas some are in your local memory, and bringing them into cache is faster. So pages have weights, and you can look at weighted paging, okay, where to bring a page into cache costs its weight. And that's also a generalization of, that's also a special case of K-server. So what's the distance between 2 points P and Q in weighted paging? The difference in weights. So at the end of the day, I'm going to pay the sum of all distances. So it's actually the average of the weights. You can set it up to be WP plus WQ over 2. Right? So when you sum all the moves, the over 2's add together and you get WP, I guess except for the very last thing. But you can sort of augment the problem so that you always move somewhere that's, you always start somewhere with weight 0 and in somewhere with weight 0, let's say. Okay. Okay. Good. And that also definitely uses the primal dual framework. That was done by Bonsall, Bookbinder, and Naor in Fox 2007. They get a log K competitive ratio for weighted paging. Okay. Okay, good. So let me now go to primal dual. So the online primal dual framework. So primal dual, in the context of just algorithm design, especially approximation algorithms, is much older than Bookbinder Naor. But the application of it to the online setting to get good bounds on competitive ratios, I believe, is due to Bookbinder Naor. This is Bookbinder Naor well, the journal version is in '09. I think it's math something rather, some operations research journal. Well, definitely the conference version is ESA '05. I'm forgetting the journal version. Okay. And before I talk to you about the primal dual framework, I need to explain, remind you about linear programming. Okay. So first off, we need a linear programming recap. I'm going to call LP for me stands for linear programming or linear program depending on context. So we want an LP looks like minimize a linear function of x. So c dot x. C is a vector, x is a vector. Subject to some linear constraints, subject to ax is less than or equal to b. A is a matrix, x and b are vectors, and x is non-negative. Coordinate-wise, component-wise, that's right. So in fact, I'm not going to do it, but in fact, you could imagine different kinds of constraints here. Like some of the components you want it to be less than or equal, some you want greater than or equal, some you want equality. You could imagine also not having this non-negativity constraint. That would be a more general class of LPs. Okay, but in fact, any program with linear constraints can be converted to this form by introducing possibly some number of new variables. So, okay, so maybe I'll put that in the homework. I don't know, but so for me, this is an LP. Okay, and their framework works for what's called covering and packing LPs. So we say an LP is a covering LP if all entries of A, B, and C are non-negative. Okay. And how many people have seen LP duality or know what a dual means in LPs? Okay. How many people have not seen LP duality? Okay, so some people have not seen it. Okay, so let me now give you a little. I don't want to just define the dual. I want to motivate it. So corresponding to any LP, there's another LP called the dual LP. Okay, and what is duality all about? So basically, so here I'm solving for x. I want to minimize over x. This is over x, not cover x. Now, suppose I want to say that I want a lower bound on the minimum. I want to say that no matter how you choose x, I promise you that you cannot make C transpose x smaller than something. I want to get the best lower bound I can on C transpose x, where x has to satisfy these constraints. What's a systematic way of proving to me that you cannot do better than this? So let's write this out. So we have our LP, which says we want to minimize the sum over I of Ci xi such that, let me write it as Cj xj, such that for I going from 1 up to m, So remember, so think of A as being an m by n matrix. So here we have A being the matrix Aij, where I goes from 1 to m, and j goes from 1 up to n. We have that for all I, the sum sorry, I meant to say this is at least b, at least for the way I want to phrase it. Okay. I mean, I mentioned in LPs it's equivalent. You could always just multiply both sides by -1. But I'm putting all LPs in this form, and then I say that it's a covering LP if this is true. Okay. So for all rows of A, I want to make sure that the dot product of the ith row of A with x is at least bi. So the sum over j from 1 to n of aij xj has to be at least bi. And also for all I, xi is at least, or for all j, xj is at least 0. Okay. Now, I want to prove to you that you cannot minimize this beyond a certain threshold. So what's one way to do it? One way to do it is to multiply both sides of inequality I by some value yi. Right? As long as yi is non-negative, the direction of this inequality doesn't change. Right? Now, furthermore, there's going to be one such yi for every inequality, and then I want to add up all these inequalities over all I. Okay? When I add up these inequalities over all I have, on the left-hand side, I have some linear combination of the x's. Right? Okay. So suppose I introduce this y. So I'm saying now that is basically, so if I sum them up over all i's, that means y transpose ax is at least y transpose b, where I have, as before, x is bigger than or equal to 0 coordinate y's, and also y is bigger than or equal to 0. As long as y is bigger than or equal to 0, I don't change the sign of the inequality. Now, this, what is this? This is some dot product with the x vector. This is equal to A transpose y transpose x. Right? So what I've just shown is that this implies that A transpose y transpose x is at least y transpose b. Wouldn't it be great if this vector in here, if A transpose y, wouldn't it be great if that were equal to c? Then I would have just proven to you that no matter what you do with your x, no matter how you choose x, c transpose x will be at least y transpose b. I've proven a lower bound on how well you can minimize this. Right? So, in fact, it doesn't even need to be equal to c. But suppose that I show you that A transpose y is at most c coordinate-wise. That would also prove a lower bound, because x is non-negative. So if A transpose y dot x is big, then C dot x definitely is also big. So that gives rise to what I'll call the dual linear program, which is try to find the best lower bound you possibly can. This is the lower bound. So the dual looks like you want to maximize your lower bound over y. Maximize B transpose y subject to A transpose y is at most C, and y is at least 0. Okay. And by the way, if A, B, and C are all bigger than 0, this is called, in the literature, this is called a packing LP. Okay. So the dual of a covering LP is a packing LP. So theorem, this is called the weak duality theorem. It says that if opt P is the min value possible in, this is called the primal. So this is called the primal, that's called the dual. If opt P is the min value possible in the primal, and opt dual is the min value possible in the dual, what's the inequality that we've just proven? How can you relate opt P to opt D? Opt D is a lower bound of opt P. That's exactly how we define the dual. The dual is a way of getting lower bounds on the primal. Then opt P is at least opt D. This is called weak duality. Yeah, max. I got a little carried away with carries. OK. So good. So the way the primal dual framework is going to work for us is we're going to write down an LP to capture whatever we're trying to minimize. So for ski rental, minimize the number of dollars you spend. Okay, and as I'm going to show you, every day when you decide to either rent or buy, a new constraint is going to be introduced into the LP. And you have to make sure kind of online that these constraints are satisfied. Okay, and you're going to do it in such a way that you kind of work with the primal and the dual at the same time, and you compare your primal solution with the dual. Okay, so if that sounds vague, it will be less vague very soon. There's also something called strong duality, which says that in fact, as long as these things are finite, they're bounded, then the primal actually equals, opt P actually equals opt D. We're not going to need that today. Okay, but we might see it again later. So ski rental, and let's say that it lasts for k days. Okay. And let's say renting costs $1, buying costs $B. So what do we want to do? So x is going to be in 0, 1. And it's going to tell us, did we buy the skis? And zi is going to be in 0, 1. And did we rent on day I? So what we want to do is so the LP looks like this. We want to minimize, well, bx plus the sum I from 1 to k of zi. Subject to, for all I from 1 to k, we either had to have bought or had rented that day. X plus zi had better be at least 1. And to fully capture the problem, we need these inequality constraints. Zi is either 0 or 1. X is either 0 or 1. Those kinds of constraints are not allowed in an LP. So we're going to relax the problem, so it won't exactly capture the problem. And we're just going to say, look, x is going to be at least 0, and for all I, zi is at least 0. Okay. What do you know? It's covering LP. Okay. And the dual okay, so as we saw, there's a mechanical way of converting the primal to the dual, right? The right-hand side becomes the cost, and the A gets transposed, etc. I'll just do it for you. So you want to maximize the sum I from 1 to k of yi, subject to the sum from I from 1 to k of yi should be at most b. And y is bigger than or equal to 0. I believe that's it. Also, y is at most 1. So for all I, yi is at most 1, and y is at least 0. So this is our packing LP. Okay. And before I give you a primal dual approach to the ski rental problem, which it's going to be overkill just to get a 2 competitive ratio, because we saw that was pretty simple. But if you want to get e over e minus 1, yeah?
If I do skis on day I, for example, how do we make sure that we also rent all of the days before day I? Because here we don't really specify what we play the skis.
Yeah, that's correct. So, I mean, the LP doesn't capture time, right? You don't know, like, yeah, I mean, it doesn't capture when did you actually buy it, okay? But the way that you should think about this is, we, the algorithm, see constraints. We see rows of A online, and whenever a row of A comes, we have to make sure it's satisfied immediately. Okay? And then after we do that, the next row of A will come. Not a new LP, but just new rows of A. So we keep seeing more and more rows of A. And as a new row of A comes, we have to set some variables to make sure the constraint's satisfied. So let me write that down. So we see rows of A online. And have to satisfy constraints online. Now, what does that mean if you're allowed to change things arbitrarily? Because I could just resolve the LP at every step, right? There's a constraint, though, which is our variable throughout the request sequence start at 0 and are monotonically non-decreasing. Okay? Because I don't want to say that you can choose to rent, you set zi to 1 on the ith day, and then way in the future you're like, oh, I really should have bought, and then I'll just change zi back to 0 and actually set x to 1. Okay, so the variables are monotonically non-decreasing. So meaning that once you choose to buy, once you set x to 1, you've bought it. Okay? Once you choose zi to be 1, you've rented. You cannot undo what you did in the past. As we're going to see, though, so here, these don't need to be integers, right? These could be fractions. As we're going to see, to get this e over e minus 1 competitive algorithm, it's going to, we're going to have to abuse the fact that we're going to set these things to fractions. Okay? And, but going back to the original ski rental problem, what does it mean to rent a half of a ski or a third of a ski for a day? We'll show that online you can also convert your fractional solution to an integral one so that it actually makes sense for the problem. But you're going to online also maintain a fractional solution. Okay. So if that's not, is that clear, I guess? So you have to maintain a solution to the LP, meaning satisfy all the constraints online as you see constraints one by one. And on the side, you also have to maintain an integral solution, which makes sense for the problem at hand. Okay, so you also have to have something that says, look, I'm not renting a tenth of a ski. But usually the way you do that is you figure out a way to solve the fractional problem online. And then once you do that, you show that actually, if I have this fractional solution I'm maintaining online, then it's possible to also maintain an integral solution online that doesn't do that much worse. This is non-decreasing. So I need a lemma, which is called approximate complementary slackness. Which says, so remember what primals and duals look like. I guess I erased the primal, so let me write the primal here. The primal says minimize C transpose X subject to AX is at least B and X is at least 0. So approximate complementary slackness says the following. Let X, Y be solutions to the primal and the dual, or the primal and the dual, respectively. Okay. Suppose there exists alpha and beta such that for all I, if xi is greater than 0, then what do we know? We know that A transpose, the ith row dot y, is certainly at most ci. Okay. But suppose it's also at least ci over alpha. So be feasible. So just to be clear, X is a feasible solution to the primal, which means it doesn't necessarily achieve the minimum, but it satisfies all the constraints. Y is also feasible for the dual. So it's not necessarily optimal, but it satisfies all the constraints. So suppose that X and Y are feasible solutions to the primal and dual, such that we can say the following. If xi is bigger than 0, then not only is the ith constraint satisfied in the dual, but it's pretty well satisfied. say alpha and beta are bigger than 0. And also for all I, if yi is bigger than 0, then not only is ai.x bigger than or equal to bi, but it's also at most beta times bi. Then C transpose x is at most alpha times beta times B transpose y. Okay. So proving this will probably be in the homework. It's just manipulation of definitions. It's not really, there's not really much craziness going on in there. Okay. But what it tells you is that if you're able to construct feasible solutions to both the primal and the dual that satisfy some properties, then you're able to say something about how good of a solution x is. Remember, you want to minimize C transpose x, right? So if you're able to compute x and y satisfying this, then you know that the C transpose x you've got is at most alpha beta times B transpose y. And why is that nice? That's nice because we know that opt of the dual is at most opt of the primal, which is at most C transpose x. Right? X is a feasible solution. So opt of the primal is at most C transpose x. And I'm telling you that that's at most alpha beta times B transpose y. Right? So remember, opt is the dual is a maximization problem. So certainly opt of the dual is at least B transpose y. Right? So what do you know? Opt of the dual is bigger than or equal to opt of the primal is bigger than or equal to B transpose y, which means this is at most alpha beta of opt of the primal. Right? I just multiplied alpha beta by both these sides of the inequality. And lo and behold, C transpose x is at most alpha beta times opt. Right? So if you can construct, what this is telling you is that if you can construct feasible solutions to the primal and the dual that satisfy these complementary slackness conditions, then you know that the x that you found is close to opt. It does almost as well as opt, up to this alpha beta. Okay? So it looks a little technical, but the point of this is to get some control on how well you're doing when compared to opt. Okay. So now, what's going to be our primal dual algorithm for to get a 2 competitive ratio for ski rental? This sounds like a real overkill, but I promise you we'll reap some benefits for harder problems. Okay, so so primal dual 2 competitive algorithm for ski rental. So remember, we see the constraints come at us one at a time. So we see a new constraint that looks like this. When constraint x plus zi is at least 1 arrives, do nothing if already satisfied. Otherwise, if it's not already satisfied, notice that when you go from the primal to the dual, every constraint in the primal becomes a variable in the dual. Okay? So there are k constraints here, right, for I equals 1 to k, and each one of these constraints corresponds to a yi. So what we're going to do is otherwise increase yi until some dual constraint becomes tight. What dual constraint can become tight? Either yi can become 1, or this sum can equal b. Okay. And then what do we do? Then set, and now again, constraints here correspond to variables there. So some constraint became tight, which corresponds to some variable in the primal. We're going to set that variable to 1. What does that actually mean here? These constraints, yi's at most 1, correspond to the zi's in the primal. So if this constraint became tight, if yi actually became 1, we'll set zi to 1. If this constraint became tight, we'll set x to 1. So then set corresponding variable in the primal to 1. Okay. And then definitely at the end of the day, we have integral solutions, okay, for the primal, which are feasible, and we have a solution to the dual, which is feasible, right? Because we don't go beyond a constraint being tight, so we're not violating any constraints. So at the end, we have a pair of feasible solutions for the primal and the dual. Okay. So now I want to say we satisfy certain approximate complementary slackness conditions. So we have to look at what happens if we have a positive primal variable. How much are we off by? What happens if we have a positive dual variable, strictly positive? How much are we off by here? Well, let's look at the variables in the primal. What if x is bigger than 0? If x is bigger than 0, that means that at some point this constraint became tight. Okay? So if x is bigger than 0, this constraint is exactly tight. There's no slack, right? Which corresponds to alpha being 1. If zi is bigger than 0, that means also this constraint is exactly tight, yi equals 1, which again corresponds to alpha being 1. How about in the dual? What if yi is bigger than 0, strictly bigger than 0? If yi is strictly bigger than 0, all I know is that, well, x plus zi is certainly at least 1. We're going to set one of them to 1. But we might end up setting both of them to 1. So it's certainly at most 2. So alpha is 1 and beta is 2. OK? So we're out of time. Next time, we'll get a little bit fancier and show how to get this e over e minus 1 with a randomized algorithm. And we'll do online set cover.